National Park Service Arrowhead text Great Basin National Park. Space Science Telescope Institute logo. 3
Welcome to Great
picture-in-picture
Basin's
screens
2020 Astronomy
with
Festival.
Ranger
My
with
name is
mountains
Ranger
in the
Charlie,
background,
and I am excited
and
to
scientist
welcome our
with
guest
James Webb
speakers
Telescope in
from the Space
background, and
Telescope Science
scientist
Institute in
with Nancy
Baltimore,
Grace
Maryland,
Roman Telescope
Dr.
in
Alex
background.
Lockwood and Dr. Brandon Lawton. If you have not viewed their talks on the James Webb and the Nancy Grace Roman Telescope, those can be found at Great Basin's YouTube channel in the same place you found this video. Now, we're here to talk with our guest speakers during this virtual program about the questions that you all asked on our social media in our little virtual program called Ask the Experts Space Telescopes Edition. So what we're going to do is we're going to work our way through some questions that were asked on both our Twitter, our Instagram, and our Facebook page to our two guest speakers, and we'll see what they have to say about these new exciting space telescopes, the James Webb and the Nancy Roman. So you guys ready?
Yep.
Alrighty. So we had a whole slew of questions, but a lot of our questions, people wanted to know the differences between all the different telescopes that we keep talking about on our social media and your guys' social media. So the first question we have is, what's the difference in the capabilities between the planned James Webb and Nancy Roman and then the existing Hubble? And what kind of questions do scientists speculate those new capabilities will answer?
Well, so I'll start off. Hubble has been up in space for 30 years. It's taken beautiful pictures. It's found out amazing things about all different parts of the universe, from planets to stars to galaxies to the early universe. And one thing that all of these telescopes have in common, Hubble and Webb and the Nancy Grace Roman Space Telescope, is that they will have the opportunity to study all sorts of kinds of astronomy, not just planets, not just galaxies, but everything like Hubble has. One of the big differences between Hubble and James Webb and the Nancy Grace Roman Telescope are that Hubble is a predominantly visible telescope, so it sees in the universe basically the same colors, the same rainbow that our eyes see. But Webb and Roman, those telescopes are keyed into different wavelengths called infrared, which are longer wavelengths than what our eyes can see. So there's actually light our eyes can't see. Infrared wavelengths is what we perceive as heat. So when Webb and Roman look out into space, instead of seeing what our eyes can see, they're actually going to see the heat signatures from planets and galaxies.
Yeah, and I'll just add on to that for Nancy Grace Roman Space Telescope, that so when NASA launches these space telescopes, they're really meant to do they have unique capabilities. They're meant to do unique things and have unique explorations. And as Alex was saying, Hubble observes a lot in the visible, and it also has a unique window into the ultraviolet universe as well, which is really our only view of the ultraviolet universe from space at that quality. And so Hubble is going to keep going as strong as it has been. We're expecting it to do great science for this decade and so on. For Nancy Grace Roman, the big capability, the big change that's different from Webb and Hubble is that Roman is a survey telescope. And so what that means is that essentially Roman has a big eye on the sky. So if you think about, let's say, Hubble, when Hubble points at an object, it really sees very little of the sky. So if you imagine holding, for example, a dime at arm's length, the amount of sky that Hubble can see in one pointing is the area of the eyeball on the president of that dime. Okay, that's how much area of the sky Hubble can see in one pointing. Okay, Roman can see 100 times that in one pointing and has similar data qualities as Hubble. So we're going to really be surveying large patches of the sky with Hubble quality data. And the amount of data we're going to get back from Roman is going to be it's going to be astronomical, pun intended.
Well, to piggyback onto this question, I think what a lot of our attendees to the festival have experience with or have seen before is looking through those backyard telescopes. Some pretty incredible backyard telescopes, up to 27-inch Dobsonian, some really big light buckets. But I'm sure the question is reaching around in their head, what's the difference in what they're seeing in their backyard telescope, say a high-end 11-inch telescope, compared to what you guys are pulling out with these two new telescopes and also with Hubble for the last 30 years?
I think if you think of what Hubble has seen around Saturn and Jupiter, I think that really gives you an idea of the difference in capabilities. You take a very nice telescope, a nice backyard telescope, even a kind of small professional telescope, 24 inches or whatever, and you look at Saturn, you're going to see the rings, you're going to see the object, but you're not going to see the colors and the patterns. You're not going to see what Hubble can see. Those pictures of Saturn, I think, are a really good example of the difference between a telescope out in space with a very large mirror. Well, Hubble has a reasonably large mirror, and so then you take something like James Webb, and we're also going to be able to look at Saturn, and we're also going to be able to see that incredible amount of detail and clarity, but we're going to be seeing even more differences than what you see with the backyard telescope because of the infrared wavelengths. And so it's going to be the same Saturn, but a completely different looking picture.
Yeah, and the only thing I'll add to that is, aside from the extra ability to see other wavelengths that you can't see from the Earth, your backyard telescope, most of them at least, probably do not have adaptive optics. They probably are not able to overcome the turbulence of the atmosphere, and that's what makes the stars twinkle. So by putting even Hubble as a visible light telescope, even putting it above Earth's atmosphere, the image quality gets a lot better because you're not having that fishbowl effect, if you will.
Yeah. Great, thank you. So then another thing a lot of our visitors are very accustomed to are those beautiful pictures. Probably the one that strikes me the most, that I remember the most, is the Pillars of Creation picture from Hubble. And so the question was, what kind of pictures are we going to get? What kind of screensavers are we going to get out of Nancy Roman and Webb?
Well, I think Roman is the easy, obvious one to answer.
So yeah, so we've actually done a comparison in Hubble in visible and near infrared, and I'll let Alex talk about like what you'll be able to get in the infrared. What Nancy Grace Roman provides, in addition to what Webb and Hubble will do, is it's going to provide that full contextual view around the area. So, with the Pillars of Creation, you saw those beautiful pillars, but that's one small area of this big star-forming complex. And with Nancy Grace Roman, you're basically going to fill in that whole picture and see what's going on outside of what we saw with Hubble.
And then specifically for the Pillars of Creation, for example, with Webb, you're going to have that same beautiful level of detail, but in infrared wavelengths. And what that means is James Webb is tuned into two different kinds of light. Near infrared, we call it, and mid infrared. They're both infrared light, but near infrared gives us the opportunity to see through dust. There's a lot of dust out in space. It's actually what is used to create planets and stars and everything that we know of. But just like a dense fog in the morning, we can't see through dust in space with our eyes, but we can see through it with near infrared wavelengths. And so there's a beautiful image that Hubble has taken, because Hubble has a little bit of near infrared capability, of the Pillars of Creation side by side in visible wavelengths and in near infrared wavelengths. And you can actually see stars forming inside of those pillars. And so the pillars themselves are beautiful, but when you can see through them and see into young stars and planets forming, that gives us incredible scientific knowledge. And so you're going to get really beautiful pictures seeing through those dust and seeing all those stars. But then when you go to mid-infrared wavelengths, you're actually going to see those columns of dust fluoresce. Because at mid-infrared wavelengths, all of that dust that's out in the universe creating things comes to life. And so the pillars of creation, you might see hot gas emitting and gives you all those beautiful colors from the different molecules and what's out there. When you're looking at the dust in mid-infrared wavelengths, you're going to see those pillars come to life in different colors, and you're going to see how warm they are and where they are. And then you can put that information together of where the dust is and where the stars are forming to really understand how things are created out there. You know, it's going to give us opportunities to understand what the original material is and how we come to stars, planets, you know, and life as we know it, really.
So these two telescopes are, from what I can see, are the new wave and the new frontier of learning about astronomy and learning about the universe and learning about the cosmos. What were the key advancements in the technology of the Webb and the Roman compared to the Hubble that allows them to have that next step up in learning about the stars?
Well, I'll point to this screensaver I have here as my background. You can see that James Webb looks completely different than Hubble. That's because since we're looking at infrared wavelengths, longer wavelengths, in order to get the same clarity, those beautiful images that Hubble had, that resolution, that detail, to get the same clarity for infrared wavelengths, you need a much larger telescope. So this mirror right here, this giant gold mirror, it's gold because that's most reflective at infrared wavelengths. This giant gold mirror is 21 feet across. And we could not put a 21-foot mirror into a giant tube like you have in your typical telescopes. Typical telescope has a mirror, an eyepiece, and then a long tube protecting that mirror and blocking off all the other light. For James Webb, in order to put this thing into space and be able to actually get it up into a rocket and out into space, we couldn't put a giant thing around it. That would be too heavy. So we had to design this tennis court size sun shield. It is 5 layers thick, and it's the size of a tennis court. And it blocks the light from the sun and the earth, all of that heat from the sun and the earth, to protect the mirrors so that the mirrors can be sensitive to light from far away in space. This sun shield was a completely new technology. It actually folds up, and there's a little video of it in my talk that is also online. It folds up to fit into the rocket, and that folding technology is brand new, something we've never done before. And then it goes out into space and it unfolds. All of that technology is brand new. We've never done this in space. We've never put a segmented mirror into space. We've never put this giant sun shield foldable thing. And so it really, in order to make James Webb happen, it is completely new technology.
Yeah, and I want to second that. So for Nancy Grace Roman, so the Roman Space Telescope is basically the same size as Hubble, and actually the mirror of Roman was gifted by another government agency. And so when you look at James Webb and then you look at Nancy Grace Roman, essentially the technologies and the things you see on James Webb were really, a lot of it invented, entirely new inventions. There hasn't been a mirror that size in space, certainly a segmented mirror like that from Webb. For Nancy Grace Roman, really the new technologies are in the instruments on board Nancy Grace Roman. There's two instruments on Nancy Grace Roman. There is what's called the wide field instrument, which is that really big eye on the sky camera. And basically they needed to find a way to pack 18 really sensitive detectors into one camera to have that big eye on the sky. And that's something that's brand new, and that's going to basically to be able to read out all those detectors all at the same time and to deal with that data volume is something that we haven't done from space before. And then the other new technology on Roman is actually, it's not labeled a science instrument, it's a technology demonstration instrument, which is a next generation coronagraph. Now, Hubble has the coronagraphs, Webb has coronagraphs. The coronagraph on Roman is meant to be a test bed to get us to really the kind of coronagraphs we want in the 2030s. Now, what a coronagraph does is it allows you to block out the light from a star so that you could actually visually see other planets going around that star. And where astronomers want to be in the 2030s, 2040s is we want to have the technology to use a coronagraph to see essentially Earth-sized planets around stars. Now, to get to that point, which is really hard to do, we need sort of an intermediary coronagraph, and Nancy Grace Roman Space Telescope is flying this sort of next generation intermediary coronagraph to see if we're able to get to that next step.
Can I mention one more cool thing?
Yeah, absolutely. Cool things are always welcome.
One of the things that really excites me about Webb is that in terms of, as Brandon was mentioning, the instruments, we have a near-infrared spectrograph called NIRSpec on board. So what a spectra does is, instead of taking a beautiful image, which we all love to see, images only give us so much information. When we really want to understand properties like what something is made of, how fast it's moving, how far away it is, we really need to get a spectra of it, which is basically, it's like a rainbow and has a lot of information in it. So every time, on Hubble, we do take spectra, we do get information about objects, but Hubble can only look at one thing at a time and get a spectra of it. And that takes a lot of time, and there's only one Hubble, and so you can only do so many objects to study. On Webb, we're putting the first the first multi-object spectrograph in space. So what does that mean? It means that Webb, for the first time, we're going to put something out there that can look at 100 objects, more than 100, but about 100 objects at once and take spectra simultaneously. So we're basically 100 times faster in getting information about the sky. We can look at 100 stars, we can look at 100 galaxies, and the technology to do that, it's like there's 248,000 little windows that have to open and close on command in order to get 100 spectra at once. And it's the first time we've ever done it in space. And it's just increasing the amount of information that we get in once by a factor of 100. And so it's really impressive, and it really, as a scientist, it gets me really excited for all the data.
Yeah. Great. So kind of down the same pathway, we have a question of, why does the James Webb Telescope look so weird? And I think you, Alex, you kind of touched on that a little bit. But I also want to note to that, someone put in a comment saying, "Am I the only one that sees a Star Destroyer in the picture of the James Webb?" But if you had anything more to add about the design and why it looks so different compared to telescopes that we know of to today.
Yeah, I'll clarify that a little bit. So it's gold, it's not silver. The mirror in your house is silver because our eyes see visible light. Silver is the most reflective to what our eyes see. That's also why Hubble is silver. James Webb is gold because gold reflects infrared wavelengths the best. The reason that it looks the way it does, and kind of like a Star Destroyer, you have light from a distant object, it comes and it hits these 18 gold segments, all of which focus that light onto a secondary mirror that's right here. And then that secondary mirror collects all of that light from those 18 segments and focuses it into the back of the telescope where the instruments are to measure that light. If we wanted to put something this big if we wanted to create something this big and make it like a typical telescope and put a cover around it, that much material would just be too heavy to send into space. It's just impossible. Just to make James Webb, they had to use a very, very lightweight but strong beryllium structure for the whole backplane of the mirror here, just to get it, light enough to send into space, just the mirror. But putting something around it would be impossible. It would be too big to fit in a rocket, and it would be way too heavy. So they had to design something to protect the mirror from especially sunlight, but that also could fold up to fit inside a rocket. Basically, we had to start from the bottom because what we wanted was just too big to fit in a rocket to send into space using any amount of fuel. Um, and so it has all the basic same components of a typical telescope. It has a large primary mirror. It has instruments behind the mirror. It has a secondary mirror that focuses the light. All of those things are usually in a typical telescope. You just don't see that tube. Instead, that tube is replaced by a giant sun shield.
Great. I think our next question can go to either one of you. Someone was curious about Hubble, so we're going back 30 years now. When Hubble was first put into space, it had a flaw that had to be corrected. What was the flaw, and how did that flaw happen?
Sure. So it's funny, you have to grind the mirrors of these telescopes very finely, and basically what happened was for Hubble, there was essentially miscalibrated equipment that was grinding the mirror, and the result was such that there was an aberration that was basically, or an error in the thickness of the mirror. There was basically 1/50th the thickness of a human hair, but that little amount of aberration basically made it so that Hubble's vision of the universe was a little bit blurry, if you will. Now, it was still, even with this blurry vision, it was still a world-class telescope in the sense that it could still do amazing science. But, they spent a lot of money to put it above the atmosphere to get rid of that blurriness, and then they added the blurriness back in because of this miscalibrated equipment. So they wanted to fix it because they really wanted this to be what it should be, right? And so essentially what they did was, astronauts went up and they essentially repaired Hubble. And the way they did that, the analogy people often say is they put contact lenses on Hubble, but essentially what they did was Hubble has many instruments. They put essentially a contact lens or a way to refocus the light properly in the telescope so that those instruments could see properly, could see it clearly. And then one of the instruments they swapped out, their main camera, they swapped out with a new camera that had that new optics built into that camera. The new camera was WIFPIC 2 is the acronym, but it was a workhorse camera on Hubble for many years, and that was essentially the way to repair the vision of Hubble. And I think there's a nice segue here actually to James Webb and sort of the way that James Webb's mirror is segmented.
Yeah, one of the questions that we get a lot is James Webb is there potential for James Webb to have the Hubble problem? And the answer is 100% not, which is really good because James Webb is too far to go fix like we did with Hubble. But you can see if you look at James Webb, there's actually 18 different segments. Part of this is because it's so big, it would be almost impossible to make one mirror that was 20 feet wide. But the more important part is that each of those 18 segments can move individually. They have each one has 7 different parts on the back, so it gives it several ranges of motion. So when you're focusing on an object, whether it's nearby, like Mars, or whether it's very, very far away, like the first galaxies in the universe, you can move all of those mirrors to get exactly the right focus. So James Webb will never be out of focus because we can focus all of those mirrors in real time.
Yeah, and you guys read their mind because that was the next question. What if it has the Hubble problem?
Never.
Never, absolutely. Yeah. Fingers crossed, never. But I do want to elaborate on something, or at least Alex, have you elaborate on it. Why is it so important that it doesn't have the Hubble problem? Where is this telescope going to be located? And also, Brandon, I have no idea. Where is Nancy Grace supposed to be located as well up in space?
So James Webb, I believe they're both going to L2. Is that correct? Yeah.
Yeah.
So Hubble is about 500 kilometers away from Earth. So, just a stone's throw. James Webb and Nancy Grace are going to be about 1 million miles away. a little bit farther. It's actually almost 4 times as far as the moon is. And it is at a point called the second Lagrange point that, because of the physics of the gravity of the sun and the gravity of the Earth, things can kind of hang out in space. They're not going to be pulled into the sun or the Earth or orbit around the sun and the Earth uniquely. So there's a stable point where some things can hang out, and it's especially important for James Webb to get far enough away from the sun and the Earth so that the heat from the sun and the Earth don't affect its measurements. And so that's why we have to go so far away with James Webb. And for Roman, I think it's a similar thing of being an infrared telescope. It's sensitive to the heat from the Earth and the sun, and so you have to get out there.
Yeah, that's right. And Roman has the extra difficult, with that wide field of view, the closer you are to Earth, the more opportunities you are for Earth to just get in the way. So the further away you are, the better opportunity you have to be able to take these sweeping views of the universe.
So is it fair to say this point that is being put out about 4 times away from Earth as the moon, is it fair to say this point is kind of a gravity neutral area, and that's why it's not going to be pushed and pulled? It's a gravity neutral area? Okay.
Exactly.
Wonderful. So I think we maybe have time for one more question, and I think it's the question that pertains to our visitors the most, especially our visitors who come here with their big telescopes and they want to see more. They always want more. They always want to know more. Will the public be able to view through the telescope through something like a live stream or data dumps from these telescopes?
So I will take first crack at that. And the quick answer is there's not going to be a live stream through the telescope, because the way the telescopes work is they collect data. The mirrors basically collect the light, and then it gets put onto a camera, an instrument, and it collects it, and then it has to send that data back to the Earth at periodic times. And so there's not a sort of a live stream. You don't look through it like you look through a backyard telescope. It's basically a camera that's open and collecting photons of light for long periods of time. But I will say this, that all of the data that NASA collects, and this is true for Webb, Hubble, and Roman, do go on publicly available archives. These are publicly funded space telescopes. The archives are all publicly funded. All of the data can be accessed by anybody that wants to do it. These big telescopes, their data is all collected on what's called the Barbara A. Mikulski Archive for Space Telescopes. That's a mouthful. We call it MAST for short, M-A-S-T. But that's the archive that basically houses it. So if you do a search for MAST archive, you'll find that. Of course, it does take some know-how and understanding how to deal with astronomical data. It's not just, the pretty pictures that you see on that we put out in press releases. It's just the raw data, typically. But that's all to say that all the data is available for anybody. And what's really great about this is that, you think about it, it's a bit of a democratizing aspect of astronomy that we're able to do this. Anybody in the world that has access, that has internet access, can do astronomy. So it doesn't matter, what sort of university or public institution you go to, whatever it may be, you can get this data and you can use it to do science.
Anything to add to that, Alex?
No, it's exactly right.
Nailed it. Great. Well, before we come to a close here with our virtual program, I have a question of my own, and it's a question I get all the time. In a normal year, I do astronomy programs 3 times a week, with anywhere from 150 to 300 people at each program. And the question I almost always get is, what is my favorite object in the night sky? So I want to throw that question to you guys as well, to answer, what is your favorite object in the night sky, understanding you guys might have the ability to see a little bit more than we do.
Well, okay, so yeah, it's a tough. I've actually never really thought about this, but I'm gonna give you two answers. One.
Okay, I'll take 2. That's fine.
One is Cassiopeia is a constellation. I just love being able to find that in the night sky. It's really easy to identify. You can see it from most latitudes, even with some light pollution. And then the other one I'll say is the Helix Nebula, because that was the first, when I was an undergraduate student, that was the first object that I kind of, programmed into the telescope. You're talking about like a 18-inch telescope that we had at our university, programmed in, found it, and really saw something that was way out there for the first time with some detail. And that was just an aha moment for me. So.
Wonderful. Yeah, those aha moments are what we go for when people are out here with their backyard telescopes. That's what we're going for. Brandon?
Yeah, I feel like I'm going to say sort of a quintessential Hubble response first, and then I'll get to my favorite. But the deep field is the deep field. You have to mention the deep field as being sort of one of those groundbreaking images that has changed our understanding of the universe. And then sort of really my personal favorite. Well, I like anything with space dust, so I like dusty things, so that's why I love Webb, and I also love Roman, because they're going to be looking at these dusty things. And one of my personal favorites is what's called the red rectangle. It's this really interesting star, and if you look at the Hubble image of it, it's got this dust, and it's got these really interesting sort of reflections and things happening with the light that gives us this really beautiful shape, and it's a very sort of different object.
Wonderful. Great. Well, guys, thank you so much, Dr. Lockwood, Dr. Lawton. Thank you so much for joining us on this virtual program, and we hope that everyone is excited, as we three at least are, about these new telescopes and what these new telescopes are going to bring to us as the human race. And you guys can continue, our viewers can continue to follow the progress of the Space Telescope Science Institute. Do you guys want to put a plug into where they can follow your guys' progress?
Yeah, so we have two sites for Webb. One is web.nasa.gov, and the other one is webtelescope.org.
Wonderful, great. Well, thank you all for coming to this virtual program. The Great Basin Astronomy Festival of 2020 is still going on. There are some in-park programs, but most of them are on these virtual programs online. You can find a ranger at the Visitor Center between 9 o'clock and 5 o'clock p.m. if you do have any questions about the festival. Thank you so much for visiting Great Basin National Park, and we hope you guys enjoy the stars.